Good day, ladies and gentlemen. We are all welcome to our lecture number 4 on Eeen202, which is electronics, measurements, and transducers. Our lecture today is going to look at what we call bipolar junction transistors, that is BJT. And a transistor is an electronic component that has 3 terminals, and the terminals are called collector, emitter, and the base. 3 terminals: base, collector, and the emitter. And the transistor is always set into operation by applying a proper current at the base terminal. We said it has 3 terminals: the base, the collector, and the emitter. And if you want your transistor to start operating, you supply a proper value of current to your base, and the transistor will now start operating. Therefore, the parameter that controls the operation of transistor is a current, and the point at which it is applied is the base of the transistor. And this transistor is of different types. The first one here is called the photo transistor. The photo means light. Therefore, this is a transistor that operates based on the light energy. And unlike the ordinary transistors that have 3 physical terminals with connections, that is base, collector, and the emitter, this one, it has only connection at the collector and the emitter. But the base is not having any physical connection, but rather we have an area at the base where when light energy pulls on it, it will produce the base current required for the transistor to start operating. So this base now, it is an area of the transistor that collects the photon energy, that's the light energy, and this light energy brings about the breakage of the bonds, which makes the carriers to be generated, and hence a current is produced. And the amount, the magnitude of the base current generated is directly proportional to the intensity of the light incidenting on the base, meaning whenever the intensity of the light increases, the amount of base current is also going to increase. The photodiodes, if you can remember, we have seen them in our lecture number 3. And these photo transistors that we are discussing now, they are mainly used in opticals as optical switches and in optical fiber communication principles. Those of you that are in electrical or communication or computer, they are going to learn much more about this at the higher level, starting from 300 level. So now let us go back to the basic bipolar junction transistor, which we said it has 3 terminals, and the terminals are called base, emitter, and the collector. And how are these terminals formed, or how is this transistor designed? What they do, normally they get a piece of pure wafer of either silicon or germanium, and at one end they inject it with either n-type impurity, that is group 5 elements, or if they wish, they can inject it with what? Group 3 elements by the process we call doping. So the area where it is highly doped, we call it an emitter, and the next, which is intermediate, is called the base, and it is moderately doped, while the other end is our collector, which is lightly doped with the impurity. So in this way, we can have either NPN transistor or PNP transistor, depending on the types of impurities we have at our emitter, our base, which is in between the two, and the collector at the other end. And for us to understand this, these are 2 symbols we use representing the block of transistors. If you look at this one, here I have N, at the middle I have P, and at the other end I have another N. Therefore we call this one NPN transistor. This extreme end is our emitter terminal. This one that is at the middle is the base terminal, and the other one at the other end is the collector terminal. And you can also look at this one where we have P-type semiconductor at the first place. Then in the middle we have our N-type, and at the other end we have P. So we call this one PNP transistor. And these are the electronic symbols we use for representing them. If you look at this here, I have a base which is at the middle, my collector is at the other end, and this end that has an arrow is called the emitter, and it is the direction of this arrow we use to differentiate NPN transistor from the PNP transistor. You see this one, the arrow is pointing out, and this is the NPN type. But this one, the arrow is pointing in, and we call it and this one we call it PNP transistor. So we have already explained that the BJT transistors are constructed using single crystal, using single wafer of either silicon or germanium. And we said one end is heavily doped, we call it the emitter, and the other end, which is middle, is medium, the intensity of the concentration of the impurities is intermediate, and that is my base. And the other end is slightly doped. That's the level of concentration of impurity is very small, and that is my collector. Now, this transistor, for us to use it in different applications, we have to configure it in a form of circuit. That is, we connect it together with other components. So based on this reason, the transistor circuit has three basic configurations. There is what we call common collector configuration, there is common emitter configuration, and we also have what we call common base configuration. And now let us start looking at these configurations one after the other. Let's say the first one is common emitter configuration. What do we mean by a transistor when it is said to be in common emitter configuration? It simply means that the emitter terminal is connected to the input and the output terminal at the same time. Look at this diagram. If you look at this diagram, this is VBB, which is a voltage being applied to the base, but the negative terminal of that voltage is connected to the emitter. And if you look at this, VCC is a voltage connected to the collector, but its negative terminal is connected to the emitter. So in this case, we can say the emitter is connected to both the input and the output. And for this reason, we call it a common emitter configuration. This one is the configuration where we are using NPN transistor. And if you look at this one carefully, you can see that it is the negative terminals of these voltages that are connected to my emitter. Now, the same diagram can be drawn, but using PNP transistor. And if you notice this, the polarity of the batteries has changed, meaning the positive terminal of this VBB and the positive terminal of VCC are the ones being connected to my emitter terminal. But in each one, we say the transistor is in common emitter configuration. Now, whenever a transistor is in common emitter configuration, we can now plot a relationship between the output current, which is the collector current, and the input output voltage, which is the voltage between the collector and the emitter terminal. And we do this plot using different values of the base current, which is the current controlling the operation of the transistor. And if you look at this diagram, we call it characteristic curve of our common emitter configuration. On the vertical axis, I have my collector current in milliamp. On the horizontal axis, I have my VCE, that's voltage between the collector and the emitter, and it is measured in volts. And these graphs where we have different lines, each line is representing different values of my base current. And if we look at this carefully, we can see that there is a lower part here, and we call it a cut-off region. And this is a region where the amount of base current supplied to the transistor is not enough to push the transistor into conduction state, and we call this one cut-off region, where the transistor is not operating. And between this end of the cut-off to this terminal, we have what we call active region. They are the ranges of different values of base current, where if they are applied to the base of the transistor will be in conduction. And when the transistor is in conduction, we said it is in active mode, and this region we call it active region. And above this active region, we have another region which is called the saturation region. And this saturation region is just a region where the current supplied to the base is even too much, that makes the transistor to start operating as if it is a superconductor that is experiencing a zero resistance. Now, from this plot, we also have what we call a load line, and this load line is nothing but a diagram or a straight line that is drawn on this characteristic curve, which we use to locate a point we call the quiescent point. And the quiescent point of any transistor is a point where the transistor is now ready to accept any external signal and act on it. And going back to the diagram, we can see that this is the straight line drawn here, and at the middle we selected a point, we call it Q. So my corresponding current at that point, we call it quiescent collector current, and the corresponding voltage, we call it quiescent voltage between the collector and the emitter, and my Q is my operating point. And how do we locate these 2 points to draw the line? We use this equation, which says IC is equal to VCC minus VCE all over RC plus RE. Now, using this graph, if I want to draw my straight line, all I need to do is to find a point where it is on this vertical line. Whenever it is on the vertical line, the value of my VCE should be equal to 0. And to locate the point when it should be on the horizontal line, and wherever we have that, my collector current is equal to 0. So now, making my collector current equal to 0, I'll find that the value of my VCE is equal to the VCC, which is the external voltage supply. And when I say my VCE is equal to 0, the value of my collector current should reduce to VCC all over RC plus RE, because this VCE in this equation should be equated to 0. So using these 2 points, I will draw my graph. Here I have VCC on the VCE axis, and here I have VCC all over RC plus RE on the vertical axis. So if we understand this, the next thing is to look at the second configuration, which we call the common base configuration. And the transistor is said to be in common base configuration when the base terminal is connected to input and the output of the transistor. And look at this. Here I have PNP transistor, and I have a battery here, VEE, which is supplying the voltage to the emitter terminal, but the negative terminal of that voltage is connected to the base. And here I have another supply, VCC, which is the voltage being supplied to the collector, but this time around its positive terminal is connected to the base. So I can say this voltage and these are both connected to the emitter base. Therefore, this is said to be in the common base configuration. This is for the PNP. And if you look at for the NPN, the only thing that changed are the polarities of the battery. This one reversed and also this one reversed. And in each case, the base terminal is connected to both the input and the output voltages. Therefore, we say our transistor is in common base configuration. Now, we also draw the characteristic curve of the transistor in common base configuration, and as we have discussed under the common emitter, you can see that on my vertical axis here I have the current, which is IC, and on the horizontal axis I have my voltage. This time around it is VCB, not VCE, because the other one is common emitter, but this one CB, common base. And the currents that we use here in drawing these different curves, they are not IV, but rather they are IE, that is emitter currents. And as we have seen in the other one, I have my cutoff region where the value of my IE is not enough to trigger the operation, and I have a range of values. We call that active region, where the transistor is in conduction mode, and we have a saturation region where the current is too much and the transistor is in like a superconduction mode. The last one is what we call the common collector configuration, and it is given here. If we look at these two diagrams, I can see that I have two voltages, this one and this, and this voltage is connected to the collector, and this one is also connected to the collector. Therefore, the collector terminal is common to both the input voltage and the output voltage. And also, if we look at this one, this is for PNP and this is the version for what? NPN. Just understanding one is sufficient to understand the other. The only thing that differentiates them is that in each case, changing from PNP to NPN will reverse the polarity of the batteries. So if you understand this, the next thing is to look at the transistor operation parameters. whenever you want to buy a transistor from electronics store, you want to use it for any application, there are some parameters that you have to check and see whether they will serve your purpose, your application. Because if you take a wrong transistor and give a different parameter, it may not function the way you want it, or it can damage your transistor the moment you start using it. And these parameters are given in this table. The first, the transistor, its collector emitter voltage is always specified, VCE, collector base voltage, VCV, emitter base voltage, VEV, and the collector current, which is IC, and the power dissipation, that's the maximum power that transistor can be subjected to, PD, and also the temperature at which it can operate, TJ, that is the junction temperature. If you subject it to any temperature beyond that, it can have problem. And here I have my amplification factor, which is beta. This amplification factor, we also call it the gain of the transistor. Different transistors have their different gains, and the gain of any transistor is the ratio of the output current to the input current. So if you understand this one, the next thing is to look at different applications of the transistor in electronics engineering. We use transistor basically in three places. There is signal amplification, there is oscillation, and there is switching techniques. So we start looking at the first one, which is the transistor as an amplifier. An amplifier is nothing but a circuit that increases the input voltage to a level or to a higher magnitude compared to the input. That is, the output is larger than the input signal. And the transistor is operated in active region when we want to use it as an amplifier, and it is the only active component in our design. In electronics engineering, we have two categories of components. One are called active components, and the other ones, they are called passive. The active components are those components that can accept signal, change its shape by either amplification or changing its nature from AC to DC. But the passive component cannot change. The only thing they can is to pass the signal by either attenuating or allowing it to pass, depending on the level of their resistance or the level of their impedance, if they are reactive components. So the transistor amplifier is of different classes. We have class A amplifier, class B amplifier, class C amplifier, depending on how it is biased. For you to see this one in clearer picture, you have to register on the level and you take the electronics engineering 310. That's where you can see all these classes and why they are called so. And also they are of different power output levels. We have low signal amplifier, we have power amplifiers which can amplify a very large amount of current or power. And the simple transistor amplifier is given here. If you look at it, this is my transistor and it is the active component amplifying the signal, and this is the source where my input comes, that's from the base, and this is the source at the terminal, collector terminal, where I take my output. Just compare the input and the output. They have the same waveform, that is the sinusoidal, but the magnitude, the amplitude of this one is much smaller than this one, therefore the output has been amplified. And we have a collector here, we call it the blocking capacitor. Its function is to make sure that all the DC components in the signal are blocked, only the AC are allowed to pass. And these two resistors, RB and RC, they are biasing resistors. Their function is to supply the required voltages and the current to the base and the collector. And this collector, we call it a coupling collector. Is the collector we use for matching the impedance of the output of this transistor at the collector and the input impedance of the device we are going to drive, like an amplifier or so. Now, for us to design a transistor amplifier, we always select a quiescent point where it will be operating, and for us to arrive at that quiescent point, these are the equations we use. To calculate the base currents, we use VCC minus VBE all over RB, where base current, as I have already said, It is the current that triggers the operation of the transistor so that it will be in operating mode, it should be in conduction mode. So in selecting the value of our base current, we use this formula where this VCC is the external supply and BBE, we call it the cut-in voltage. That's the minimum voltage for the transistor to start conducting, and typically it has a value of 0.7 for the silicon transistor and 0.2 for the germanium transistor, and this RV is the base resistance that regulates the amount of current. And if I want to find my output current, I should multiply the base current by the gain, that's the beta, the amplification factor, and the quiescent point voltage VCE is obtained using this equation, that is VCC minus ICRC. So the power that the transistor can produce when it is used as an amplifier is given by this formula, that is P0 AC, that's the output power, alternating current, is equal to IC square RMS value times what? RC. IC is the collector current, which is the output current, times what? The RC, the resistor there. You can either leave it like this or say VC square all over RC, using the voltage now as the collector, all over the resistor of that collector. The transistor is also used as an oscillator. And what is an oscillator? Oscillator is an electronic circuit that has the ability of accepting AC DC signal and changing it into the AC form. So, and changing it into AC form. And the oscillator is different from the amplifier in such a way that it does not need any external supply. What it does is that the DC that is applied to it for biasing is part of that DC it is going to use in order to change it into alternating currents. And for the operation of transistor to continue, we need a constant feedback, because it is part of the output signal that is now taken through the feedback network to operate the transistor in oscillation mode. And for us to make sure the oscillator is operating normally, there is another condition apart from the feedback. That is the gain of the amplified oscillator should be equal to 1. What are we saying? The value of the output signal must be equal to the input signal. So if you divide the two, it should give you 1, and that is your gain. And also we have different types of transistor oscillator, which includes the Colbit, the phase shift oscillator, the Hartley oscillator, the crystal oscillator, and many more. All these things, they are going to be speciated when you reach 300 level in 310, that is electronics engineering. And the typical circuit diagram showing transistor operating as an oscillator is given here. This is my active component, and all the resistors and my capacitors, they are used for either biasing the circuit, thus supplying the voltages and currents required, or they are used for oscillation, creating the frequency at which it oscillates. And the formula we use for calculating the frequency of oscillation, F is equal to 1 over 2 pi RC, where 2 pi is constant. You are the one that will select your R and C, times 1 over square root of 4 plus 6 plus 4 into RC all over R. Now, selecting the values of these ones, you can come up with the frequency at which you want your transistor to operate. So the last application of a transistor is it is used as a switch, and we know the function of switch is for on-in and offing some devices or systems. And the transistors used in this case, they can be either NPN or they can be PNP. And these are the two basic diagrams of transistors as switches. If you look at this, it is PNP transistor because the arrow is pointing in. So my switch is here. Whenever the switch is open, there is a high voltage going to the base, and the PNP transistor requires a very low voltage for it to start operating. So whenever you close this one, you are now given a path for the voltage from this to go to the ground, thereby making the base voltage here very small. So this one will activate and it will drive our relay. But in the case of NPN, it requires high voltage before the transistor works. So therefore our switch is now located here. When it is opened, nothing is coming here from the battery. but the moment you close it, the voltage will come here. Some will go this way, some will go this, and the one that goes here is the one that will activate my transistor so that it will drive the relay. So these are the three basic applications of transistor. It is used in amplification, it is used in oscillation, and it is used for switching application. So this is the end of today's lecture and lecture number 4, and I thank you very much for your time. I advise you to watch this video over and over again. Whenever you have any problem, feel free to contact me for clarification. Thank you very much. Meet you in the next lecture.